It's time to talk about research and about the exam. Okay. So what am I going to expect of you at this exam? I think we talked about this in the very beginning. The exam needs to be the presentation, the study, and the research, and the presentation and the simulations of a paper, conference paper, journal paper. I'm prepared. I think I have already prepared, but I have to just slightly adjust a list of 10 or 11 papers on Moodle, numbered from 1 up to 11. Each of you must pick only one paper independently. The papers should be different from each other. Okay, so I would kindly ask you not to be two people presenting the same paper. The only degree of freedom I'm allowing is that you do not necessarily need to present the papers I've prepared for you, but you can also come up with your own examples. If you find papers, research papers, in the field that contain model reduction or modeling or reduced order modeling and model approximation and such, okay, you can feel free to do that. Okay, feel free to do that. Okay, so I'm imposing, there is no restrictions from my side. Okay, there is no restrictions from my side. But what I'm going to ask you is, you need to pick a paper and you need to send me a message on the group, either on the WhatsApp group or here in Teams, telling me my name is, and you state your name, and I'm picking paper number 1, 2, 3, 4, 7, 12, 11, and so on and so forth. Or please allow me to present this paper because this subject is highly related to the topic of this lecture. Okay. Then starting probably in the 9th week, you can come and graduate and finish this course, and you can present the paper. Week 10 during the course, of course. Week 9, 10, 11, 12 through 14. And also at the exam date, okay, because we're going to set a date for the exam. Furthermore, I need you to, if you want to get more points and get good grades, you need to solve the assignments. I noticed 3 submissions for the second assignment. It's not much, but it's something. I'm going to check them out pretty soon, and I'm going to grade them for you. Okay? You'll get grades for these assignments. Okay? How did you find the assignment number 2? I don't think it was very difficult because essentially most of it we've discussed last time. We discussed most of it last time. Yeah, that's true. Would you agree? Was it difficult to solve?
No.
Okay. All right. Fine. If you have any questions about the exam setting. Any questions, please? I suppose everyone's happy about the exam. I'm going to post an announcement on the forum of the Moodle, as well as the group, okay, the WhatsApp group. I'm going to post an announcement about the exam explaining the things I've just told you. Okay. This is a research master, hence I expect you to present me some research. Okay. It's not going to be one of those regular exams where you get exercises and I'm going to check and grade the exercises. No. You need to prove that you can research in this topic. You can do some research in this topic. So you need to make a report about what you have understood, what you have not understood, your feeling about the paper, your feeling about the methods and the theory presented. You need to simulate the examples, if any, and explain the issues you encounter. Okay, this is research essentially. Furthermore, the assignments are along the same, follow the same arguments. Okay, all right. Do we agree about this? Okay, do we agree or not?
Yes.
Okay, fine, thanks. Okay, let's carry on. Okay, so last week, after finishing the discussion about the realization problem, which is quite important, okay, we started to discuss. We started to discuss and to tackle, or to try to understand and to study the notion of a linear matrix equation. Okay, because the matrix equations are very important for the following topics. Okay, and we need to understand how to fix and how to solve them and how they behave, how their solutions behave. The main linear matrix equations we encounter are the Sylvester equations, which are quite general, but they're quite popular in control. They stem at every step in control algorithms. And then the Lyapunov equations follow. The Lyapunov equations being particular instances of the Sylvester equations. Okay, and both of them have solutions, and we discussed here the solution. Their solutions are in general called Gramians, and we are going to use this important notion of Gramians starting today, okay, and see how this notion works for a model reduction procedure. Okay, so we do have the Sylvester equation, the Lyapunov equations, and we remember also from the previous chapters, that these equations are very important for stability, first of all. And then their Gramians, after stability, their Gramians are going to be used in a model reduction procedure. Okay. So a Lyapunov equation we see here, ax plus xa star plus bb star equals 0. This is the equation for the controllability Gramian, and there is the counterpart of the equation for the observability Gramian. Okay, and if you notice this discussion about positive, negative, and zero eigenvalue, positive. I was right, because their solutions are symmetric matrices or Hermitian matrices. Since they are symmetric, their spectra are real spectra. Okay, so the eigenvalues are real. So we had some powerful, nice results about when there is negative, positive, or zero eigenvalues for the Gramian. And we noticed that when the Gramian has only positive eigenvalues and some other assumptions are met, then this implies the stability of the matrix A. So the stability of the matrix A is a necessary, and it can be proven. It was proven in the second chapter, that stability, okay, is actually in a one-to-one relation with the number of positive eigenvalues of the Gramian of the matrix. Okay. Okay. So one last ingredient we are interested in, and we'll see that this is quite important to understand, and this is crucial for model reduction and for modeling in dynamical systems in general. It's the eigenvalue problem. Okay, so a matrix possesses a set of invariants that uniquely determine the matrix. One set of invariants are the eigenvalues, which form the spectrum of the matrix, and the second one is the singular values, okay, which are also quite crucial. Okay, the singular values help in a lot of things. We'll see that in the balanced truncation method, especially. They are quite relevant. Furthermore, the maximal singular value is very useful as well, giving a certain measure for the matrix. So what is the eigenvalue problem? What's the eigenvalue problem? Okay, so again, let's recall the definition. We recall the definition. Let A be a n by n, let's say, real matrix. Okay, then lambda in the complex plane is an eigenvalue of A, and this is denoted by saying lambda belongs to the spectrum of the matrix A, if and only if there exists an eigenvector V, okay, non-zero, belonging to Rn, such that A minus, or lambda I minus A, lambda I minus A V equals 0. Okay, so V, which is an eigenvector, is actually in the kernel of lambda I minus A. Okay. Okay. Now, this being said, we now need we do remember that the eigenvalue is the root of the minimal polynomial associated to the matrix. Okay. So we start with the eigenvalue problem for a square matrix and show further its connection with the Jordan canonical form. So we need some canonical forms to emphasize and compute the eigenvalues, and also the notion of invariant subspace. Okay. Okay. Fine. Let's call here we F. So we do not need to constantly switch and swap between complex numbers and real numbers. We call them F, all of them. Okay. So F stands for the Fn stands for the vector space of columns with n elements in F, and F P by M is the set of P by M matrices with elements in F. Okay. Any matrix in a natural way, any matrix n, square matrix n in Fn, represents a linear transformation from Fn into Fn, and I would say here n as well should be, to be a coordinate transformation, can also needs to be invertible as well. Okay, so the problem furthermore, the problem to solve, to find the complex eigenvalue lambda is the problem of solving an nth degree polynomial equation that lambda I minus n equals to 0. Okay, and this is called the eigenvalue problem. And chi lambda, this is the Greek letter chi. Okay, chi. Chi lambda is called the characteristic polynomial of the matrix n. Okay, so furthermore, we are talking about non-degenerate matrices in the sense that the characteristic polynomial is also the minimal polynomial of the matrix n. And furthermore, due to they say here, to the fundamental theorem of algebra, any nth order nth degree polynomial has n complex roots, also counting multiplicities, okay, which are called eigenvalues. So the eigenvalues of n are the roots of this polynomial that lambda I minus n. Okay. The union of the n eigenvalues is called the spectrum, and is noted, they denote it here by lambda n, sigma n, whatever. It's the same thing. Okay. It's just the reunion of all the eigenvalues of the matrix n. Okay. All right. For an eigenvalue lambda 0 of n, they say here, there always exists a non-zero vector called the eigenvector of n, okay, which is such that nx is lambda 0x. So this is essentially the definition I just presented you a minute ago of an eigenvalue. This is the definition, essentially. And the solution of the polynomial equation is the characterization, the polynomial characterization of eigenvalues. Okay. Precisely, it says here, if n is non-singular, there always exists a unique matrix called the inverse of n, denoted by n inverse, such that n, okay, so here we say that n is invertible, okay. The identity matrix, okay, for square matrices to introduce the, okay, we introduce the relation of similarity of matrices, which we used quite a lot. You notice that in dynamical systems, we use coordinate transformations all the time, okay. This similarity transformation is always associated to the change of the basis in Fn. So please note that these are notions of linear algebra, okay, which all of you should be familiar with, irrespective of your economic or engineering background. These are fundamental notions for any student working in sciences or areas or something like that, that are related to figures and numbers. Okay. Okay, so essentially this coordinate transformation is changing the basis of the space Fn. Okay. Okay, so thus any x in Fn changes to x tilde tx, and n in n tilde represent the same linear transformation from Fn into Fn with respect to two different choices of a basis. So essentially, the space is identical, but the generating basis of the space can be different. So you can write the same space in different, or represent the same space in different coordinates. And we have been doing that quite a lot, especially when we're talking about controllability and observability, and about controllable and observable decompositions or structural decompositions, as well as minimal realizations. Coordinate transformations were and are crucial. We'll notice later on that in the sequel, when we discuss about balanced truncation is also based on a crucial coordinate transformation, such that the system, the model, the dynamical part, the dynamics of the model, are represented in a specific way that allows us to study something and to draw some conclusions about the relevant, or the more relevant and the less relevant dynamics of the system. Okay. All right. So we have been using that now. So now it's just a recap and just fixing the notions. We are talking about the Jordan canonical form of a square matrix. This is also or it should also be something quite familiar to you. Okay. Okay, so if the space F is the set of complex numbers, the similarity equivalence 33. Let's see who. Okay, so this is 33, the classic coordinate transformation. Induces a canonical form on the set of n by n matrices with complex element called complex Jordan canonical form as follows. So what is a complex Jordan canonical form? Okay, consider n a square nth dimensional matrix, or a square matrix of size n, and consider lambda 1 up to lambda k be a set of k distinct eigenvalues, okay, but each with its multiplicity. Okay, so each of these eigenvalues has a specific multiplicity. Okay, then there always exists a coordinate transformation that brings the original matrix n into a specific form, emphasizing on the main diagonal the spectrum of the matrix. This is wonderful. This is such a powerful result. So, okay, so here is two things which are quite important. First of all, keep in mind that no matter how many no matter how many changes of coordinates I apply successively, the eigenvalues are the same. So essentially, in other words, the eigenvalues of a matrix are invariant to coordinate transformations. And this is something we are quite familiar with, and this is something which is quite relevant because otherwise none of what we've been discussing up to now is useful any longer, unless this property holds. And this property holds by default for any matrix in this world, so to speak. Okay? So there's always a coordinate transformation T, an invertible matrix, such that T and T inverse is another matrix called N index capital J, where N index capital J is the diagonal matrix of these matrices, these block matrices. These are block matrices. Okay, so N11, N22, N double K of lambda K. So for each eigenvalue, or to each eigenvalue, we associate a block NII. So to any eigenvalue lambda I, we associate the block N double I. Okay, containing in its turn, yeah, these diagonals, another diagonal matrix of and other diagonal blocks, okay, where JS of lambda I associated to lambda I is the Jordan block, or the elementary Jordan block associated to the eigenvalue lambda I. Note that the dimension of JS, okay, the dimension of JS is the multiplicity, is given by the multiplicity of the eigenvalue lambda I. Okay, is given by the multiplicity of the of lambda I. Okay, so for instance, if you have a matrix, yeah, let's see a matrix, consider a matrix A of order 3, so to speak. Okay, and you have lambda 1 is 1 and lambda 2 equals lambda 3 is -1. Okay, then there exists a coordinate transformation T, okay, invertible, such that TAT inverse is 1, and then the block -1, -1, 1, 0. You see, this is multiplicity 1, multiplicity 1, multiplicity 1, and this is multiplicity 2. Okay, so this is a block of dimension 2 for the -1, and this is a block of dimension 1. Okay, so this is J1, and this is J -1. Okay, J -1. These are elementary blocks. Okay, so the set of distinct eigenvalues lambda 1 through lambda k, together with a set of block sizes Sj, where I is from 1 to k and j is from 1 to hi, completely determine, they say here, the complex Jordan canonical form up to a permutation of blocks on the main diagonal. What's that supposed to mean? That's supposed to mean that means that I can find another coordinate transformation T tilde, okay, a permutation, okay, such that this is -1, 1, -1, 0, and 1. I can have the same. I can have it like that. Okay, I can have it like that. Okay, and so and also other shapes as well, other diagonal shapes as well. Okay, so for a given eigenvalue lambda I, the sizes Sj are called elementary Jordan indices or partial multiplicities. Okay, of the eigenvalue lambda I. The positive integer hi is called the geometric multiplicity, and the sum ni, which is si plus up to hi in upper index between brackets I, This is the algebraic multiplicity of lambda I. So these are delicate notions. I understand they are not very easy to process, of the specific multiplicities of eigenvalues. You can have algebraic multiplicity, which is the easiest to understand, and you can also have geometric multiplicity. So what is the real Jordan canonical form? Okay, hold on. Before that, the sum ni, which is s1i plus up to shii, is called the algebraic. Okay, multiplicity, and as a root of the characteristic polynomial. Okay, the root of the characteristic polynomial. Now, this was the complex Jordan canonical form, but you can also have a real Jordan canonical form. We consider now an n, a matrix, the same matrix n. However, this time having real entries and not complex entries. Okay, but real entries, which is the real case in engineering and also economics. Okay, we use matrices with real entries, real coefficients. Okay. Okay. Now, a matrix n does not necessarily have n real eigenvalues. However, it has n complex eigenvalues. So this is the case which is interesting for us. The previous case was the case of a complex matrix. Which is a bit more complicated. But we are not going to use complex matrices per se, because the models that we get are 100% made of real parameters and real coefficients. Okay, so it's only fair to discuss and to study the real Jordan canonical form for matrices with real entries. Okay. However, even if the matrix is real, okay, it may not necessarily have only real eigenvalues. As we know, it can also have complex eigenvalues. Moreover, n complex eigenvalues. Okay. And they say here the non-real eigenvalues always occur in complex conjugated pairs. That only makes sense. Okay. So you can have -1 plus j, -1 minus j. If your matrix is of order 3, you can never have -1, I don't know, plus 2j. And this is not possible this is possible for a complex valued matrix. However, it's impossible for a real valued matrix. And this is also due to the fundamental theorem of algebra, because since the matrix has real elements, okay, it's a real valued matrix, the characteristic polynomial is a polynomial with real coefficients. Once again, the fundamental theorem of algebra is telling us that even such a polynomial has n eigenvalues, okay, has n eigenvalues, and but these eigenvalues, we have to be careful because they can come in complex pairs, complex conjugated pairs, or real values. And if they are mixed, because this is usually the case, that the spectra are mixed, complex eigenvalues and real eigenvalues, we have to be careful that the complex ones are always in complex conjugated pairs. Okay. Okay. So this makes the treatment of canonical forms and the real similarity transformation somehow different, he says here. So this is a bit different from what we discussed so far about the coordinate transformation for matrices. Consider the matrices to be in a spectrum of this form. Okay. Lambda 1 through lambda r are real eigenvalues. Lambda r plus 1 through lambda k and the rest of them, lambda r plus 1 through lambda k, are complex eigenvalues, and also they're conjugated. Lambda r plus 1 conjugated through lambda k conjugated also occur in the same set, eigenvalue set. Okay. Okay. Hence, if we restrict the similarity transformation to have real elements as well, of course, since we deal with real matrices, of course, that it only makes sense, it's only natural that the coordinate transformation is also real valued. Otherwise, things do not make sense at all. Okay? We get the real Jordan canonical form if we use real coordinate transformations, nj of n, where nj is in 35. Okay, have this 35. Okay. NII, okay, has the form 3637. Okay, so NII, they also have the same form. All right. And as the form for real eigenvalues, while the non-real eigenvalues, say alpha I plus j beta I, where alpha I and beta I are real numbers and beta I is non-zero, we have this form of the NIIs, okay, where JS is a 2S by 2S elementary matrix of this form, okay? Okay, so this is an elementary real Jordan blocking. This K alpha I beta I, they're usually real valued matrices containing the real and the negative, the real and the imaginary parts of the complex eigenvalues. And Ki have this specific form. This is the typical form of a matrix with two second order matrix with two complex conjugated eigenvalues. Why? Because if you just pick that of lambda I minus k alpha I beta I, this is the determinant, okay, of lambda minus alpha I minus beta I, so the signs change on the skew diagonal, lambda minus alpha I. And if you compute this determinant, this is lambda minus alpha I square plus beta I square. Okay, so this is lambda square plus 2 alpha I lambda plus alpha I square plus beta I square. But this is the determinant of Ki, and this is the trace of Ki. It only makes sense. And what are the eigenvalues? Okay, so you set this to 0. Okay, and then you have delta is minus 2 alpha I plus minus j. Oh, no, sorry, delta, not the square root. I was wrong. So delta is 4 alpha I squared minus 4, 1 times alpha I squared plus beta I squared. Okay? And this is what? This is more minus 4 beta I squared. So this is always negative for all beta I real. For all beta I, sorry, not positive, but real. This is negative. Okay? So if this is negative, then we have two complex conjugated values, and lambda 1, 2 is alpha I, sorry, is 2 alpha I plus minus 2j beta I over 2. So, surprise, such matrices always have the eigenvalues alpha I plus minus j beta I. Always, for all alpha I and beta I real and beta I non-zero. This is what always happens. That's why we can always, if we want to express complex eigenvalues for a real valued matrix, and we only want to have the Jordan form to be a real matrix, not a complex matrix, we always have to use this form. It makes sense, doesn't it? Makes sense?
Sure.
Okay. I'm glad you agree. So it's clear from the above discussion that two similar matrices always have the same Jordan canonical form. And now the final discussion of basic notions, of fundamental notions required for further studying model order reduction techniques. It's the notion of an invariant subspace of a square matrix. So the concept of an invariant space of a matrix is the same. The definition is: consider a matrix to be a square matrix, complex or real valued. The linear space calligraphic V subset Fn, subset the nth dimensional space, is called an invariant subspace if any multiplication n times any element of V, of calligraphic V, is a subset of, is also included in V. Okay, so this is equivalent to saying that alpha times V also belongs to Fn for all V in V and A in F. This is an invariant set. And there are a couple of examples here. The simplest examples of an invariant subspace are the eigenvectors. The eigenvectors of a matrix satisfy this property. Why? Why would you say that? What is an eigenvector? If lambda is an eigenvalue of A, then by definition, there exists the eigenvector V such that, look at the property, AV is
0.
lambda V. True? This is the definition of an eigenvalue. We all agree on that, right?
Yes.
We all agree on that. Now this AV being equal to lambda V, so if V, V is in Fn, lambda V, where is it? In Fn as well. So this generates the eigenvector of a matrix, generate an invariant subspace for the space Fn. So this is the simplest example at hand. Okay. It's easy to see that if V, they say here, is an invariant subspace of dimension L, because the dimension of the invariant subspace need not necessarily be N. It can be L. Then we can split. We can find the similarity matrix U, split accordingly, L and N minus L. Okay. L invariant and N minus L variant, so to speak. So there exists with V in the image of U1 such that UAU has this specific block triangular form, where we can emphasize in A11 the L part, the invariant part. Okay, the invariant part. The spectrum of this matrix is the reunion of the spectra of the block diagonals. This is something typical for triangular and block triangular matrices. Equation 42, that is. So in the new coordinate system, V is represented by this guy because A22 is not invariant. But in the first part in L is invariant, so it has to be IL here. So V is in the image, the space V, calligraphic V, is the image of the matrix identity L and 0. So the matrix A and its spectrum restricted to the space calligraphic V are always defined by the matrices A11, okay, and the spectrum is the spectrum of the matrix A11 respectively, okay. What conversely, 42 holds for non-singular value U, then V is in the also the image of U1 and is an invariant subspace of A, and so conversely, if this holds, for any U satisfying this property, there is always the space calligraphic V, which is the image of U1, which is the image of U1, okay, which is the image of U1. Okay, consider the partition of the complex plane in two disjoint sets, the good and the bad one, CG and CB. An invariant subspace is CG is the good one, is CG invariant, okay, if the spectrum lies in CG, okay, if the spectrum lies in CG, okay. So if lambda 1 reunited with lambda 2 is the whole spectrum of the matrix A, and this is a partition of the spectrum of the matrix A, we always can find an invariant subspace given by lambda 1, okay? This is something that follows immediately from the Jordan canonical form and all the discussions we had above. At this point, I'm going to remind you that you can read about these things in any linear algebra book, as well as the Antulas book that you have on Moodle. Okay, so you can read all about these things. Okay, that's like a handbook. So the first chapters of that book, those chapters are just like a Bible for the idea of dynamical systems and all the linear algebra and linear algebra geometrical aspects related to it. So if you ask me, I kindly advise you to take that book in your hands and read it if you're interested in a bit of linear algebra, if you really want to understand these concepts or not. If not, no one's forcing you to do that anyway. It's up to you. So all of this, okay, if A has real elements and lambda 1 is a symmetric set with respect to the imaginary axis, we can choose, okay, so, okay, we can choose the subspace V to be the whole Rn of dimension n, okay? Furthermore, if the spectra are disjoint, lambda 1 and lambda 2, then this choice of the V is unique. And now, to sum up everything about this little recap of linear algebra, we present an important result which might be useful for later understanding some details, okay? Because even so, we are using these even if we do not. I'm presenting all these things to set the, if you like, the legal framework or setup for the things I'm going to talk about in the sequel. So things are clear and things are nice. We are not going to give proofs because it's not our job here, unless maybe only one proof we're going to present because it's constructive. For the rest, there is no need to do that. So the following result, now we need a characterization, okay? We gave the definition of our invariant subset and a few properties. So it's only fair now to get a characterization of an invariant subspace in terms of matrices, because matrices are the more definite thing we can get our hands on. Spaces are difficult. They are very abstract. Matrices are also abstract, but they are more real. We can understand them better than the subspaces and the spaces and the subspaces. So we present the following theorem. Consider an a squared matrix. If the space calligraphic V is the image of calligraphic V, a subset of Fn, and this is an L-dimensional invariant subspace of A, where V is the basis for A, then there exists another matrix S such that AV, please note the dimensions. AV equals VS. AV equals VS, and moreover, S is A restricted to the subspace, to the invariant subspace V. So A is N times N. Okay, and V is N times L. V is N times L, and S is L times L. So this is quite nice. The dimensions, we know, I suppose we all know how to multiply matrices. Okay, we do not need to discuss that. Okay, we know that. Just please confirm that you know how to perform matrix multiplication. Okay, fine. So you know that in matrix multiplication, dimensions are essential, are crucial. Okay, dimensions have to match to get a proper matrix multiplication and a proper result. Conversely, if this relation, if 44 holds for a specific basis V in F in N times L, and there exists a matrix S such that 44 holds, then V equals the image of V, calligraphic V equal the image of V is an invariant subspace of A, and S is the restriction of A to the invariant subspace V. And this, of course, it follows easily from the definition of the invariant subspace. So we just apply the ingredients and everything falls into place. Right. At this point, we are through discussing the general notions and concepts of linear dynamical systems. Okay? To sum up, we have presented this object. Okay? A set of linear differential equations, okay, with states, inputs, and outputs, okay, with a transfer matrix, okay, with the X in Rn, okay. We discussed stability, okay, solutions, okay, solutions, stability, sigma A is in C minus, steady state response, okay, when this happens, and this was important, steady state response, okay, then controllability, the possibility to control the state, and observability, the influence of the state on the output, okay. Here we had Gramian's tests and decompositions, okay. Then we discussed the realization problem, okay. These are both related to Hankel matrices, okay, and other things. And finally, we discussed linear matrix equations and their solutions, okay, and also eigenvalues and invariant subspaces. So these are all the ingredients now. These are all the ingredients. The main assumption here was that X is in Rn. Okay. We started this, and let's recall from the introduction chapter. Okay, that we always assume n is very, very large. Okay, so under this assumption, okay, all of this fails in the sense that we cannot compute the results. The theoretical results hold, but numerically, it fails. Okay, think only of this. How do you assess the eigenvalues of a... You noticed when the MATLAB, you remember when my MATLAB broke and collapsed and crashed when I gave an n equal to 10,000, only to compute the eigenvalues. And nota bene, MATLAB has efficient algorithms to compute eigenvalues. It's not just solving polynomials, okay? Or how do you assess controllability and observability when the ranks fail? You notice that even on the CD player, okay, at a certain point last time, the CD player had rank 120, but with classic computations, the rank showed 118, which is wrong. Let alone that the realization problem is irrelevant, okay? How to solve linear matrix equations with these huge dimensions? I mean, there is a bunch of very nice, important algorithms, but they also fail for huge dimensions. So what to do? Okay, what to do? And what the response is model order reduction. Model order reduction. Right. Please tell me if you have any questions up to now. Questions, please. Right. Let's have a short break, and let's meet again in 5 to 10 minutes. Agreed?
Okay.
Okay. Fine. See you soon. Right, mateys, where were we? Yep. You still here?
Yeah, I'm here.
Yes, we are here.
Okay, lovely. Yeah, I just went for a sip of water, and when I came back, I did turn on the telly, and I was caught up in the bloody stupid news of today. Weird times we're living in. Sometimes I have the feeling that we are living in completely parallel worlds, okay? If you know what I mean. I mean, look at us, what we discuss here, and look at them, what they discuss there. Should be kind of the other way around, wouldn't you think? Well, never mind. Bloody idiots. So, model order reduction, okay? Let's reformulate the problem as we know it, okay? So, given A, I'm writing it like this, B, C, D of order n large, find A hat, B hat, C hat, D, they are the same. Let's call this sigma, and let's call this sigma hat, okay? Such that, 1, okay, you know, of order, I forgot here to mention, of order ni, such that 1, n or ni is much smaller than n. Let's put it the other way around. N is not n, ni is much smaller than n. 2, sigma hat approximates sigma under some constraint, right? So you have to put a constraint. What does it mean? It approximates sigma. 3, sigma hat is accurate. Okay. That said, that means that some norm, okay, is small. Okay. And 4, sigma hat is easy to compute. So these are pretty much the goals of model order reduction. This is what we want to find, okay? The question is how? How do we do that? How do we do that? Okay. What is the criterion, first of all? Okay, so the first, this one we understand. What is this one? How do we compute this one? And then, of course, we also have to address this one. Okay, so how do we do that? And we have 2 large classes of methods. Okay, we have singular value decomposition SVD based methods, and here we include balanced truncation, Hankel norm, Hankel or optimal Hankel norm, proper orthogonal decomposition, etc. And also Krylov projection methods, okay, or moment matching stemming from moment matching methods, okay, with their peculiarities each, okay, with their peculiarities each, okay. So each of them is good in some sense. Each of them is good in some sense, okay. The idea is that you always need to project your given system, your ABCD. So A hat usually, or let's make it like this. Oh, damn, Krylov. Krylov is Russian, yeah? Usually A hat, B hat, or sigma hat, let's make it generic because we call him sigma hat in general. Sigma hat should be the projection of sigma onto some subspace, okay? Sigma of order n, some space of order, sigma order n onto some space of order ni. Now the question is, who is this projection? How do we compute, and who is this projection? Okay. Right. So I prepared for you a few things about the first method called balanced truncation. Okay, balanced truncation. First of all, I'm going to present you a couple of slides. Okay, a very short version of the story, give you the main ingredients, and then we start again the story with some slides written by someone else with detailed stuff, easier for us to understand. Furthermore, we also have here an excerpt from the book. I took the liberty of taking a part of the book here, okay? So we can also go through this piece of text, okay? We can also go through this piece of text, okay? We are going to make a mix of all these things over the next couple of lectures, okay? Or maybe the next 1 or 2 lectures, so we can understand the things. Since this, again, I'm reiterating this idea, since this is a research master, I'm going to give you some idea, and then you have to research these things yourselves. I focused more on fixing some fundamental notions, making your life easier to understand these given concepts. Okay? Do you all agree on that?
Okay. Yes.
Fine. Balanced truncation. Okay? Here we have to deal, so we also have to deal here with the Hankel operator. This is related to the Hankel matrix, part of the previous chapter we've discussed quite a lot. So the summary goes like this. We consider a linear system, which is this guy we know already, and the first assumptions that we make on this linear system are that the system is minimal, okay, and that the matrix A is stable. So it's a stable minimal system to start with. That only makes sense. In general, we try to model things which are like that. Of course, there exists quite a lot of models, an infinite number of models as well, of unstable things, okay? Unstable things. But these procedures can also be adapted to those specific cases. And in the book of Antulas, there is a lot of adaptation of these techniques, and we are going to browse through these adaptations someday to be able to understand all these things. Okay, we do remember that these systems, okay, furthermore, I forgot to say here, this guy has a transfer function. This guy has a transfer function. Ks is CSI minus A inverse B, okay, which is a rational matrix, okay, of dimension n. This is a rational matrix of dimension n. Now, since this is minimal, we remember that minimal means controllable and observable. This is what minimal means. We do remember these things, okay? Controllable and observable. Since this is controllable, there exists, if you remember when we were talking about Gramians, there exists, we can define based on those guys, or we define a controllability function. What is this controllability function? Let's read this relation. The controllability function is the minimum input effort. So it's the minimum by u in L2 of minus infinity 0. L2 is the space of square integrable time functions. Okay. And this is the minimal energy given to the system in the past to control the system from 0 to x0. Okay. It's the minimal input effort required to steer the state from 0 to x0 from the past. So from minus infinity in the past until now. Okay? Until now. So this is called controllability function, measuring the input effort required to steer the state from 0 to x0, and it's parameterized in x0. Okay, so we need to measure the effort. We need to measure this effort. This is an important criterion. Okay. Furthermore, at the moment when the system reaches the initial state x0, now we set the time. So this is the time. Okay, this is the time axis. Okay. So I start from minus infinity, and here I start from 0. And now I'm in the moment t0, where I'm at the state x0. Turn off the input u and check the evolution of the system when the input u is turned off. This gives the observability function. This is the simplest version of an observability function because there is no optimization involved. This is just measuring the energy as it is of the output of the system. Okay, this is the energy. Okay, this is an energy of the output of the system. Okay, you see here u is equal to 0, so the input is turned off. We now set x0 as the initial condition. We turn off the input, we let the system freely evolve, and we check the energy of the output. So this is the energy generated by the output freely at x0 in the future, because now I turn off the input and let the time let the system evolve in time as the time goes by. Okay, so I'm looking at past input energy to future output energy. So the idea is looking at the minimum effort put in the past to bring the system from 0 to x0. Now I'm also measuring the effect of that on the output from 0 to infinity. Okay, from 0 to infinity. So these are interesting criteria: past input energy to future output energy. Past input energy to future output energy. Now, a main result, I'm not going to get into the details, but it can be easily proven if you know some optimization techniques, for instance, for LC. We can easily prove, and maybe we can see some proof of this later on in other slides and in other approaches of the same theory, and also in the book of Antulas, that the controllability and the observability energies are given in terms of the controllability and the observability Gramians. Look at the Lyapunov equations that give W and M. Please note that, and you remember, this can be easily checked in in the third chapter, okay? When we are talking about systems, in systems number 2, in systems number 2, when we talked about controllability and observability, you remember we defined Gramians. please note that the controllability function is in terms of the inverse of the controllability Gramian. Inverse of the controllability Gramian, okay? However, the observability energy function is given by the observability Gramian itself. Now, the controllability Gramian is the solution of this Lyapunov equation. Okay, so these are a couple of Lyapunov equations. Okay, as we discussed last time. So this is the these are the Lyapunov equations of the Gramians. Controllability Lyapunov equation, observability Lyapunov equations, where these equations, since A is also stable and minimal, are positive definite matrices. Please keep that in mind there, because the system is minimal, so it's both controllable and observable. Both Gramians are symmetric. Since A is also stable, check also the previous chapters, both Gramians are also, and it can be proven that both Gramians are also positive definite matrices. Okay? Positive. So the Gramians, probably the eigenvalues or the singular values of something, or the eigenvalues of a specific matrix in terms of these Gramians, okay, is giving relevant information about the past input energy and the future output energy. Now, with these two Gramians, we compute the so-called balanced realization of a dynamical system. We say that a system ABC is a balanced realization of a transfer function if the Gramians are equal and diagonal, and on the diagonal, these positive numbers are presented. These positive numbers, sigma 1 through sigma n, positive definite, okay? They are the so-called Hankel singular values of the system, and they're actually the eigenvalues, the square of the sigma I are the eigenvalues of the product Wm. Are the eigenvalues of the product Wm. Okay? All right? So now we are going to present the idea of how to measure the past input energy and the future input output energy using these invariants. Please note that the Hankel singular values are invariant to coordinate transformations, just like the eigenvalues of the system. They're also invariants of the system. What is the significance of a sigma I, a Hankel singular values, associated with the state xi? If sigma I is 0, then the state Si is neither controllable nor observable. So the state is non-minimal. So this disappears through the minimal realization problem. Okay? If the Hankel singular value is almost 0, so it's very small, then the state Xi is called almost non-minimal because it's hard to control and hard to observe. Why is that? Because in balanced form, the controllability energy is given by the inverse of the Hankel singular value sigma I for the state Xi, whereas the output energy is given by the Hankel singular value sigma I of the state Xi. So if sigma I is small, then LCXI is huge. So you need a huge amount of effort to steer the system from state 0 to state x0. And LOXI is small. And the importance of this state when you turn off the input on the output is negligible. So this is called an almost non-minimal state. So why not neglect these dynamics? This is the question. Why not neglect this almost irrelevant dynamics? This is the question. Okay. I stop for a minute here, an intermediate point. Question is, do you people understand the concepts I'm trying to fix here? How we look at things for a dynamical system? How are things until now? Do I make myself a little bit clear?
Yes, it's mostly clear.
Okay, fine. Okay. Now, so you guys probably realize that the scope of this method is to bring any ABC system into balanced form. But this is not an easy job. This is not an easy job, as we'll see. Okay, for any system, we need to build up an algorithm to do that. Okay, because you are not going to get this for free. There's going to be some costs, essentially, and in particular, some numerical costs as well. Now, let's make the relation between the controllability, observability, and the Hankel operator. Okay, consider the ABC system with an impulse response C exponential of ATB. Please do go back to the second chapter of this lecture and find what an impulse response is, because there's the whole explanation is there. A Hankel operator is an operator, it's an infinite dimensional operator, is calligraphic H defined on the L2 space of square integrable system with values in the same L2 space of square integrable systems on positive time. So it's L2 0 infinity to L2 0 infinity. And the Hankel operator is applied on an input signal U and is the integral from 0 to infinity of ht plus tau, u tau, d tau. It looks like a convolution, you see? Looks like a convolution, but it's not convolution because you don't have t minus tau, but you have t plus tau. Please note that this is not convolution. This is a Hankel operator, okay? This operator is mapping past inputs to future outputs. Past inputs to future outputs, okay? Let's see who gives this operator. But first of all, this operator is characterized by the Hankel singular values. But this operator is characterized by an infinity of Hankel singular values. And do remember the Hankel matrix. The Hankel matrix, because this is given by the Hankel matrix, is an infinite dimensional matrix. However, we can truncate starting with n, okay? Okay, so this guy has the Hankel singular values sigma 1, sigma 2, sigma n. They're all positive. And if n is the minimal order, then sigma n plus 1 equals sigma n plus 2 equal sigma n plus infinity equal what? If the minimal order is n, how much do you think these Hankel singular values are? A Hankel singular value means 0 means not controllable, not observable. And the minimal order is n. So these are all up to n are positive definite. How are these from n plus 1 to n plus infinity? How much are they if the minimal order is n? How much are they if the minimal order is n? Minimal order n means that the nth dimension is controllable and observable. So up to n, we have positive Hankel singular values. From n plus 1 further on, they all have the value what? Which value? How much are they? How much are they? Can you tell me? Can you tell me? How much? What's their value?
Infinite?
No. I just said, look at this. Look at this. Look at this part. So the minimal order, the controllable and observable part, have dimension n. So sigma 1 through sigma n is positive. From sigma n plus 1 further on, they have the value. How is the part from n plus 1, n plus 2? It's not minimal, so it's not controllable and not observable, right? So how much is sigma n plus 1, sigma n plus 2, and so on?
So it must be 0.
0, exactly. So these guys are all 0. These guys are all 0. Exactly. What took you so long? Okay, fine.
I'm sorry, personally, I had to leave for a bit. I now
no
came
worries.
back.
Yeah, I realized that you people come and go. Never mind.
Sorry about that.
No problem. It's good that you gave the good answer. So it's 0. Okay. Okay, so this is interesting. So that means that probably we are going to look at the small singular values, and we are going to probably neglect. So we are going to seek for this part and maybe neglect. This is the question. We'll give an answer to this for the model reduction. Okay, are we going to neglect this for model reduction? But let's keep talking about the Hankel operator. This is a crucial and very powerful operator for linear dynamical systems. I'm not sure, but I think you have used the Hankel operator as well when you studied, those of you who studied robust control last year. Is any of you B1? Is any of you B1?
I was B1, but I don't really remember if we used the Hankel operator.
You must have, because it's also crucial in robust control. Hankel matrices, Toeplitz matrices, these guys. You must have used it in the lectures anyway. Okay, so we have the controllability operator. Now we can define two specific peculiar operators. The controllability operator, which is called calligraphic C, defined on the input space with values in the state space. And CU, look here, it's the integral from 0 to infinity of this part. Okay, and we can also, so once you turn off your output, okay, you see that this is from 0 to infinity, but the controllability we discussed from minus infinity to 0 at this point. Okay, so that's why it's related to Gramian inverse. Okay, observability operator is from the x0 to the output space of square integrable time signals, and it has this very simple definition. This is the observability operator. We discussed this operator, but we didn't call it observability operator when we discussed the property of observability. Okay, discuss the property of observability. Okay, so the observable space or the unobservable space, if you remember, this is the kernel of the observability matrix Q, but this is also the kernel of the observability operator OX. Okay, and the powerful result, another crucial result, we are not going to give the proof of, you can find it in the books and in the other references, is that the Hankel operator is the observability operator applied to the controllability operator. It satisfies these relations. It's very interesting. It's very interesting because you remember the Hankel matrix. Do you remember this in matrix term? In matrix term. In matrix terms. Okay, infinite dimensional matrix, if you like. You remember the Hankel matrix H. Do you remember? N, you cut the Hankel matrix at N and you make it a finite dimensional matrix, was Q, the controllability matrix for in N steps, times the observability matrix in N steps, times the controllability matrix in N steps. So this is equivalent. This is what it actually says. This is the Hankel operator, and this is its matrix formulation. This is its matrix formulation. Now, why is this Hankel operator so important? Why have we introduced this notion of a Hankel operator? Why? What's the reason to do that? There must be a reason. Yes, the main reason is that we can introduce a specific energetic measure of the system called the Hankel norm of the system. The Hankel norm of the system is the maximum output energy of the Hankel operator, okay, with respect to the input effort given to the system. It has this formulation, supremum by U, okay, of the 2 norm of the Hankel operator versus the 2 norm of the input. Okay, this is a signal norm. This is a signal norm. A signal norm, and this is also a signal norm. Okay, so it's well defined. It's well defined. Okay, it's well defined because H U equals Y. Y is a signal. Okay, so this is well defined. So the Hankel norm, okay, the squared Hankel norm, is the quotient or is the best ratio between the output energy obtained with a specific control effort. With a specific control effort. This is the Hankel norm. Okay, and the funny thing about the Hankel norm is that it can be characterized, of course, they're all connected. It can be characterized in terms of the Hankel singular values. It's connected to the Hankel singular values. So the Hankel norm of this guy, okay, the Hankel norm of the transfer function Ks associated with the state space system ABC, D, anyway, D has no relevance here, is given by the largest Hankel singular value, which is the first one. This is the Hankel norm of a system. This Hankel norm is going to be useful when we are going to introduce the notion of optimal Hankel norm. Optimal Hankel norm. Okay? Very interesting result. Okay? Well, I didn't. Okay, this is not finished here. So these are the main ingredients. Okay? These are the main ingredients. So Now we have to understand the concept of balanced realization, and balanced truncation. What does this actually mean? What does this actually mean? Means that given so what we do, okay? Method. Given ABC, dimension n, transfer function Ks is C Si minus A inverse B, okay, with controllability Gramian W and observability Gramian M, okay, we compute the coordinate transformation T invertible such that we can compute A hat, B hat, C hat is TAT inverse, TB, CT inverse, such that W hat equals M hat is in balanced form, is sigma 1 through sigma n, sigma I, Hankel, singular values. So this is called balancing. This is called balancing a dynamical system. Balancing a dynamical system, okay? All right. Now, this is part 1, and part 2. This is the model the truncation. The truncation given A hat. Now we start from the balanced realization. B hat and C hat, okay? With W hat is M hat is the diagonal matrix sigma 1 through sigma n, okay? Okay? And assuming that sigma 1 is larger than sigma 2, this is what usually happens. Larger because this is the largest one. You remember, this is the Hankel norm. Larger than sigma, let's ni. Much larger than sigma ni plus 1. Larger than sigma ni plus 2. Larger than sigma n. Larger than 0. Okay. Okay. All right. We split A hat, B hat. So A hat is A11, A12, A22. B hat is B1, B2. C hat is C1, C2. Okay, with A11 in R ni times ni, B1 in R ni times M inputs, and C1 in R P outputs times ni. Okay, Okay, and we neglect this part. Okay, so we neglect all these very small, hard to control, and nothing to see at the output states. Okay, all right, and then extract A11, B1, C1, which is the balanced truncated, or the balanced truncation approximation of A, B, C. And this is the model reduction. This is the model reduction. This is not like the realization or the minimal realization problem. This is an approximation. This is not exact. This is an approximation A11, B1, C1 of A, B, C. Okay, this is an approximation. And now we have two important questions. Q1, how to build the balancing transformation T. Question 2, how accurate is A11, B1, C1 with respect to A, B, C? These are the main questions we need to answer. So what I gave you here is the main problem and the main method. Okay, now we need to explain these things in detail and construct an algorithm yielding such an approximation. Okay, this is what we have to do. This is what we have to do. Okay, all right. Okay, 2-minute break, and I'll see you soon. Okay.
Okay.
Okay, just think about these questions. Think about these questions. Uite-te acolo! Okie dokie. Okay, let's carry on, please. Hope you're still here. Are you?
Yes, we are here.
Okay, thanks for waiting. Right, so now let's look at these slides. Please notice that they are from Stanford University, so this is the creme de la creme of the higher education in the world. Stanford is in the top 5, if I'm not mistaken, or at least, or mostly top 10. So please be sure that this is the best information you can get. Okay. So I'm using these slides. I have gone through them a while ago. I went through them a while ago, so I checked them again, and I think they are quite suitable to be presented to you. So as you can see, the outline of the discussion in this piece of text is that we can recall the notions of reachability or controllability, because these notions are identical. So if you go from 0 to x0, that's controllability. But the question, the reverse question, how to recover the 0 state from a specific state, that's called reachability. How to reach the origin from a specific state, reachability. But the notions are completely identical in the linear case. However, in the nonlinear case, for instance, look at the pendulum or any other nonlinear system, the notions are different from each other most of the times. Okay, then they discuss about balancing. They show you balance truncation. They show you the error analysis. So what is how accurate is the model? Also very important, which properties does the approximation uphold? For instance, and this is very, very important, balanced truncation preserves the stability of the system, and this is crucial. This is something wonderful. So these two, the balanced truncation is famous and very popular due to these two properties. One more thing, I'm not going to go into details. Balanced truncation for systems as model reduction procedure actually is a corollary or a consequence of techniques used in system identification. Then we discuss a little bit about the computational complexity. Okay, there is a comparison with another method based on singular value decomposition. That's the proper orthogonal decomposition, called shortly named POD. Then there is an application, and then there is a combination between the two methods. Okay, so it's quite a bit of information. We're going to go slowly through part of it, and then we continue the next time. Okay, so this being said, let's go. So we consider please do not mind the different notation. So instead of x, it's the state is called w. There is no issue about that. Things are clear from the context. So we have a linear time invariant, highly dimensional or high dimensional system given by these equations, okay? A, B, C, okay? So it's still the ABC system we are familiar with, okay? ABC. With the initial condition W0, okay? N, capital N is the dimension, P is the number of outputs, Q is the number, P is the number of inputs, Q is the number of outputs. Typically in application, most application, the number of outputs, of inputs is usually much smaller than the number of states. whereas the number of outputs can be much higher than the number of states because you can measure more things, more combinations of the states. Okay. Now, we recall that the solution W of this linear matrix ODE equation, ODE, ordinary differential equation, is this function phi, depending on the time, the exogenous input U, the initial moment T0, and the initial state W0. And this is the free evolution. Okay, so this is W free. And the forced evolution, this is W forced. If you remember from chapter 2, okay? Free evolution and forced evolution for all moments of time, non-negative, okay? Now, we briefly recall from the third chapter, we briefly recall controllability, reachability, controllability, and observability. We discussed these notions in detail, but they're worth mentioning once again, so everything is fresh for the technique to be developed in this part. So a state W is reachable, you see, if there exists an input U of finite energy such that under this input and zero initial condition, the state system is W. Okay. A state, oh, so they define it different, but the definitions are actually identical. Okay, so this is how we usually define controllable, but they define it as reachable. Okay, we do not mind. The notions are completely identical, and they define controllability, the ability to recover the initial zero state if there is an input such that at a certain moment, at a certain finite moment of time t, capital T, the solution of the system is zero. Okay, so reachable, controllable. If you remember correctly, observability. Okay, so this is C x e a to the power t x0, w0, sorry. Let's use this weird w notation. Okay. A state is called unobservable if for all t non-negative, the output when the input is zero, notice that on the spot for the input we have zero, is zero. Okay, this is called unobservable. We remember that. Okay. All right. A completely controllable dynamical system. So they introduced the notion of structural or controllable decomposition from a different perspective. Okay. Interpretation. So, okay, a linear dynamical system is completely controllable if T0 if it's not equivalent to a system of this type. Okay, so if you cannot split, so they say that a system is controllable if you cannot split it into controllable and uncontrollable parts. It's a weird. It looks weird, but this is correct. This is totally correct, because if it is the system is fully controllable, this splitting makes no sense. But if the system is not controllable, this particular partition is absolutely suitable and called for. Okay. Okay. Let's see how what the interpretation of such definition is. Okay. It's not possible to find a coordinate system in which the state variables are separated into controllable and uncontrollable. Okay. Such that the second part is not affected by the first part, because the uncontrollable, if you remember correctly, the uncontrollable part of the system is not reachable, if you like, is not affected by anything, not affected by a coordinate transformation, neither affected by a coordinate transformation, nor affected by any input. That's why it's called uncontrollable, because any input that you use, the uncontrollable part remains invariant. There is no change in it. Okay. Controllability is only a property, of course, of the matrix pair AB. We remember that. Okay. They say here that the definition is extendable to time variant system. What is time variant? When the matrices ABC also depend on time, the system becomes time variant. Okay. All right. what is a completely observable dynamical system? Equivalently, so if you remember, controllability and observability are properties dual to each other. Hence, the definition is dual. A system is fully observable if there is no possibility to split the state vector into two parts. Okay, whereas one part is affected by an input, is visible at the output, whereas the second part is not at all visible or noticeable in the output. So if you cannot perform this particular partition, if there is no such partition, then the system is totally observable. Okay, note that this is dual to definition 4. This is, I think this is called 4. Yeah, this is dual to definition 4. As you can see here, these definitions and all these notions are due to, or are thanks to Robert Kalman, God rest his soul. He's the guy who invented all these very nice notions and all what modern dynamical systems and dynamical control systems are today. Okay. Similar, so we can have an identical interpretation to the one about controllability. If it's not possible to find a coordinate system where the state variables are split into W1 and W2 such that the second part W2 is not affected by the first by W1, okay? Hence, if you cannot perform this partition, hence the system is fully or completely observable, okay? Note that observability, of course, as we know, is a property of the pair of matrices C and A. And of course, this definition, again, they claim can be extended to linear time variant systems, which is not the object to discuss in this moment. There is an example here for controllability and observability. There is this electrical circuit. Okay, this is an RLC circuit. We have two parallel resistors. We have an inductance L. We have a voltage input U1. We have a capacitor C, and the output and the voltage W2. Okay, and of course on this guy we can apply both Kirchhoff laws. Okay, because we have a node in this place, and we have two loops where we can apply Kirchhoff's laws in these places. Okay. So the equation of the network in terms of the current W1, so the state, which is not measurable, so to speak, is W1, the current, okay, the current through the inductor L. We use it as output the current Y1, okay, on the first loop, okay. I think, or is it a voltage? No, it looks like a current, if you ask me. Okay, the equation of the, yeah, it's a current of the network in terms of the current W1 flowing through the inductor and the potential W2 across the capacitor. So these are potential, they are not even voltages. Okay, and under the assumption that LC and equal to R equal to 1 is given by these three equations. So this is the ABC model for this RLC circuit. Okay, we have two states, W1 and W2. We have a single output. We have also a D term, which is non-zero. Okay, and we have both equations decoupled, if you look, because they are in parallel. So they are both decoupled. The only coupling they get is in the measured output, but they are completely decoupled, and that makes it very easy, because here we get A is the diagonal matrix -1 over L minus 1 over C. This is a stable matrix. Why? Because the spectrum of A is -1 over L minus 1 over C. Okay, and if L and C are positive, actually they satisfy this relation, but L, C are positive, this is stable. Okay, because the eigenvalues are in C minus. Okay, and B is 1, 1. Okay? And C is 1 over L, 1 over C, and D, this is a scalar, D is 1. So we have identified all the matrix parameters of this system. Okay? Now, if you look at it, since this A is diagonal, it's easy to see that since A is diagonal in B has no zero elements, that the pair AB, we build the controllability matrix B, AB. Okay, so this is 1, 1, and AB is minus 1L minus 1C. Okay? Yeah? So that R is 1 over LC, so this is 1, this is non-zero, so the rank of R is 2, so the system is controllable. The same holds for observability. The matrix Q is C, CA, so it's 1L, 1C, and CA is minus 1L squared minus 1C squared. Okay, so this is easy to see. Okay, it's easy to see that this, the determinant of this is 1 over LC. I think it's 1 over LC squared, so it's still 1. This is non-zero, so this is also observable. So we cannot do the splitting. We cannot do the splitting. Okay. Now, question: if you use the change of variable, you use this simple change of variable. This is an invertible change of variable. Okay. And so W1 tilde is half W1 plus W2, and W2 tilde is half W1 minus W2. These are also some specific coordinates that we can use. In the new coordinates, W1 tilde and W2 tilde, we get this system. We get this system, okay? But in this form, W1 is controllable but not observed. W2 is, but am I making a mistake somewhere? Because I suppose they want to say that this guy is not observable. So what happened? 1L, 1C. I'm making something wrong. This is wrong. Because I think it's not observable. Is it? So 1L, 1C. So this is minus 1L squared minus 1 C squared. No. Oh, no. This is 0. I'm sorry. I made a mistake. I calculated the determinant wrong. So this is 0. This is 0. 0. So not observable. It's controllable but not observable. Yeah, it's correct. It's controllable and not observable. And the guy is going to emphasize this through the coordinate transformation. Okay, so if you look, in this guy, W1 tilde is observable but not controllable but not observable, and W2 is observable but not controllable. So we can also split it like this. Okay, we can also split it like this. Okay, in these new coordinates. Okay, so we can see here that this is not observable. Okay, so one state is observable, the other one is not. However, this is controllable, but this is no mistake. This is controllable because the B are different from 0 Okay. This is correct, yeah? No, I think also AB is not correct. No, this is correct. No, this is correct. Right? Am I doing something wrong? No. B.
The determinant of area is not the sum. Is
No, but this
minus
is. Oh. You're right. This is wrong. So this is minus
1 over C plus 1 over L.
So this is minus L plus C over LC because LC is 1. Okay. But this is not 0, huh? This isn't 0, is it?
It depends, I guess.
Well, if L equals C, yeah, but they say that L is not equal C. They said LC equals 1. Okay.
Okay.
So they're kind of not equal. Oh, I think there is a mistake here. I think it's L equal to C equal to R equal to 1. And if you have it like that, then it's indeed 0. Okay. This is 0. And then this is true, because one is controllable but not observable, and the other one is observable but not controllable. You see, this is not controllable because there is no influence of U. And W1 is not observable at the output. This is what the guy wanted to emphasize, okay? Okay. So now we get a canonical decomposition, as we know, okay? We know we can do that. So for a general system which is not controllable or not or not observable, we can perform a structural decomposition, as we know, okay? Because we can split the state in 4 parts, A, B, C, D, okay? And the sizes of these guys, they say they do not depend on the choice of bases, okay? And the matrices can take this form. The matrices can take this form, okay? And here there is an interpretation of those 4 parts. A is completely controllable but unobservable. B is completely controllable and completely observable. So B is the minimal part. We know now. We now know this. This is the minimal part. Okay. Okay. C is uncontrollable and unobservable, so C is the worst. And D is uncontrollable and observable. Okay. So there is a coordinate transformation such that we can get the minimal part ABB, BB, CB. This is the minimal part, the minimal realization of the system. We know that, okay? We studied that last time quite extensively, okay? So we can do that, okay? Here, the controllable and the reachable and the observable spaces are presented. Here we have the reachability or the observability matrix. Actually, that's why it's called R, from reachability. Reachability matrix R, we know that. This can be infinite dimensional, but we usually, for controllability up to a certain order, we stop here, okay? The controllable subspace W controllable is part of the state space, okay? And is the set containing all the controllable states of the system, okay? We know that the X controllable are all in the image of the controllability matrix R, which means that the X uncontrollable, not like in Romanian, but like in English, X uncontrollable is part of kernel of R transposed. Okay, and then kernel of R transposed plus image of R give us the state space Rn. Okay. Oh, and here it is. The explanations are here, and these are things we know. Note that the reachable subspace is an invariant subspace of the system, is the property we discussed last in the previous chapter. So the reachable subspace, is an invariant subspace of Rn. Okay. The system is completely reachable if and only if the rank is n. We know that. We have been using that. And reachability, of course, is basis independent. That is invariant to a sequence, to an infinite sequence, I could say, to any infinite sequence okay, of coordinate changes. Okay, good. Now look at the Gramians. This is Gramian in finite time. You remember that. This is the controllability Gramian in finite time. And this is the observability Gramian in finite time. Yeah, the reachability Gramian at time t less than infinity is defined as the n by n symmetric and positive semi-definite matrix, this, as well as the observability Gramian, which is defined as the square symmetric positive semi-definite matrix like this. Okay, and look, the reachability space R, which is the image of the controllability matrix, are spanned by the columns of the rank that give the rank of the controllability Gramian. Okay, so if rank P is ni, okay, then dimension of W reach is ni, and actually vice versa is the same. Okay, so the rank of the Gramian gives us the controllability subspace. If the rank of the Gramian is identical to the dimension of the system, then the whole system is completely controllable. Okay. Hence, a system ABC, so of course, it says positive semi-definite. What does this mean? That if there are any zero eigenvalues, the rank of the positive semi-definite matrix drops. Okay, so sigma p, okay, is lambda 1, lambda n, okay, and they're all lambda I like this. And if there exists ni lambda I positive definite and n minus ni lambda I 0, okay, then dimension of W reach, as they call it here, is ni. It only makes sense. Okay, so the Gramian is also a guy who can determine the controllability subspace of a given system. Okay, hence, if there is no lambda I equal to 0, and P is symmetric and positive definite at some time, then the system is controllable or reachable. Okay. As you can see, we have pretty much the same notions, but with a little bit of a different perspective. Okay, it's a good perspective because it's going to help us understand the balance truncation and the balancing procedure. Okay, equivalence between reachability and controllability, because I told you they are the same notion, but the people here state it as a powerful result in itself. For continuous linear time invariant, I would say dynamical systems, but apparently this holds for time invariant systems as well. The notions of controllability and reachability are equivalent. So essentially this property holds. Okay. All right. The same ideas apply to observability. We can define the unobservability space, which is the set of all unobservable states of a peculiar system, okay? And it's also an infinite dimensional space. However, if we have dimension n, we stop at n minus 1 in these indices. We stop at n minus 1. Okay, so we can build it much smaller or up to order n. This is, and this O is actually the Q. Okay, we denoted it by Q. This is the observability matrix of the system. This is the observability matrix of the system. And the unobservable space, we know that it's the kernel of the observability matrix. Okay, so X is unobservable, belongs to the kernel of Q. That means that Qx equals 0. And similarly, the state space Rn is the kernel of the observability matrix plus the image of the observability matrix transposed, because this is the observable part. Okay, the observable part. And again, we'll see that all the properties we have discussed so far can be easily repeated in the context of observability. Why is that? Because, or since, these properties are dual to one another. The same. It's an invariant, the unobservable space, and also the observable space. They are invariant subspaces of the state space Rn. The system is completely controllable. We know that if this rank condition holds, and observability is basis independent, or equivalently, observability is invariant to an infinite sequence, or to any infinite sequence of coordinate transformations. Okay? All right. Now, the last thing we are going to recap and fix today is we've discussed so far, and we noticed in the short version of the story about balanced truncation, the infinite time gramians, the infinite controllability gramian defined for a stable linear time invariant system. This is the symmetric semi-positive definite matrix like this. Okay, this is the controllability gramian for any stable, I didn't say controllable, keep in mind, for any stable linear time invariant system. And the same holds for observability. So we have a gramian in infinite time for controllability and another one for observability. Okay. Now, I didn't do that. This is something new. We can use, you remember we have the transfer function Ks or Ts is Csi minus A inverse B. Okay. In the theory of signals, of time signals, there is the so-called Parseval result, which is a sort of mapping between time domain and frequency domain when applying the Fourier transform. It's very interesting, and it says essentially that the energy of the signal, of the time signal, yeah, Parseval theorem, you can look this up on the internet. It says that the energy of the time signal, it's the same as the energy of the associated Fourier transform. Okay, so using this result, which I kindly invite you to look up over the internet, the two Gramians defined before can be written in terms, they can have a frequency domain expression. P is 1 over 2 pi integral from minus infinity to infinity j omega identity minus A inverse. This comes from this evaluated at S equal j omega, BB transpose minus j omega I and minus A BB Hermitian, okay? BB star j minus j omega I minus A star inverse d omega, and the observability Gramians are the same, so they have also frequency domain expressions, and this is quite interesting. And most importantly, both infinite time Gramians, as we have already discussed, they are solutions of these two Sylvester Lyapunov equations. Okay, Lyapunov equations. Okay, when do these Lyapunov equations have a solution? They have a solution all the time. Okay, they have a solution all the time because lambda of A is the same as lambda of A transposed. Okay, and you have this has a solution if lambda of A plus lambda of A transpose is non-zero. Okay, so they have a solution which is symmetric and positive semi-definite. However, if the system is stable, then the solution and also controllable, then the controllability Gramian is positive definite, and if it's stable and observable, the observability Gramian is positive definite. Okay, so we can have A stable and P and Q. Okay, all right. And these Gramians have an energetic interpretation, just like I showed you when I discussed in the short version about the energy functions. P and Q are respective bases for the reachable and observable subspaces. We can also define these semi-norms. They are not norms because they do not fulfill, for instance, they do not fulfill the triangle inequality. But for a reachable system, the inner product based on P inverse characterizes the minimal energy, so the minimal effort, just like we discussed, required to steer the state from 0 to W as time goes to infinity. Okay? Or if you look in the past, from minus infinity, the time goes from minus infinity to 0. And this is the energy. This is the energy, so this is LC. This is LC W. Okay? And furthermore, the inner product based on the observability Gramian indicates the maximal, and this is not necessarily the maximal energy. I wouldn't put the maximal here, if you ask me. The energy produced by the output of the system corresponds to an initial state when no input is, so when the input is turned off. When the input is turned off. Okay, and this is LO of W. Okay, all right. Okay, I suggest we stop here. Would you agree?
Yes.
Yes.
Okay. Right. So I told you about the exam. I'm going to prepare the papers for the exam. I'm going to prepare a new assignment for you. So please keep your eyes on Moodle, because I'm going to give you assignment 3, lab 3. Okay, because time flies. So I have to prepare lab 3 for this, for which week? We're in the week, okay, for this week. So it's almost prepared here. I have to check it and I have to open it. Okay, so keep your eyes on solving lab 3. Actually, let me do it right now. Please stay with me for a sec. Let's see, lab 3. Okay, so this is not important anymore. Okay. Okay, so this is the assignment. We have the CD player and the building. For each, extract the matrices using the command fold. Okay, so this is about the Gramians. This is about the Gramians. Okay. All right. This is about the Gramians. Okay, so let me just edit the settings. All right. Please be patient with me for a second. So we can start this guy. I'm going to start it tomorrow, April at 6 p.m. and you have until next lecture is on the 22nd. Okay, until midnight. And that's it. And now lab 3 is open and you can start making it. Okay? All right?
Okay.
Fine. Any questions, please?
I have some questions about the previous lab 2.
Yes, please.
Can I share my screen to be more clear?
Certainly.
Okay.
Please do.
Okay, can you see my screen?
Not yet. Oh, sorry. Let me go to the screen. Sorry. I think I can, but I haven't looked. Yep. Now I can see it. Yes. Right.
So the first question, there was a plot at a point to plot for the difference between the system and our approximations.
Exactly. Those weird approximations, the straight line and the simple first order system. Yeah.
But
And
this is a system which is the difference.
This is an error system. Yeah.
Okay.
It's parallel. If you do not like to build it like this, you can build this guy using the function parallel.
Mm-hmm. Yeah. Okay.
And you can see the matching in certain points. You can see the matching in certain points. Look on the body diagram. Look on the magnitude plot. You see, it matches from 0, so from 10 minus 2 to almost 10 to the power 1, and also in a point close to 10 to the power 2. There is matching, you see?
Mm-hmm.
In the magnitude plot. In the magnitude plot. And this is here probably the error. Yeah, this is the infinite, the H infinity error. H infinity error, if you remember from second year, you can read it on the border diagram of the error system, because it's the H infinity error of the H infinity, norm of a system is the supremum from all frequencies of G of the transfer function evaluated at J omega. Okay, look it up in your previous courses. Okay, so what's the question? What's the problem?
To clean me out about this plot.
No, it's all right.
Okay.
This is what I
didn't.
wanted to see. I'd like you to comment. I'd like you to comment on the results. Why is the matching here from 10 to minus 2 go to, you see, look at the magnitude plot. Why is matching there from t to power minus 2 until t to 10 to power 1? And what does this second magnitude plot show you? Why is that point equal? Yeah, try to explain that based on the notions we have been talking about. So the plots are okay.
Okay.
But try to explain the results to me in a text file or something. Okay.
The second question was about the second data set building. When we compute the DC gain, it's 0. So the method applied at the first data set is not longer suitable when we use K as
That's
DC
good.
gain.
That's good. Probably it's not true.
So we should modify it. We should
get a different system. Okay. Yes. Build another guy. Increase the dimension. Okay. So you cannot make K hat equal to a constant because the DC gain is 0. It's ridiculous to put another constant. But you can make it a first order to be close to 1 K over TS plus 1, for instance. Okay. So, and you have to play with it with K and T until you get some nice results.
Okay. So
it's all right. It's very good. But this is lab 2. Did you upload the results?
Yeah,
because
this is
the deadline has gone. Okay.
sure.
Okay. Fine. Looks fine to me.
After all, I wanted to, for my knowledge, to
for your own sake. I see.
Yeah.
Makes sense. For the sake of your good knowledge. I appreciate it. It looks nice. That's good.
Okay.
Anything else?
No, I think not.
Okay.
Thank you.
All right. Anyone else? Any questions, please? Anyone else? Any questions, please? If not, I'll see you next week. Okay? Please do lab 3. Okay? And let's keep in touch. And use the materials on Moodle, books, papers, and so on. And then I'll put the announcement about the exam, and you need to start picking your paper for the exam. Okay?
Okay.
Yes.
Okay.
Okay.
Well, have a good weekend, and I'll see you next week. Okay? And try to keep as safe as possible. Okay? And for God's sakes, do go get vaccinated, please. Okay? So maybe we can all meet someday. All right?
Today I got vaccinated.
Oh, congratulations. Yes. First jab or second jab?
The second one.
Oh, so you had the second as well. Whoa, so yes. You're fully immunized in a few days.
Yes, I think in 2 weeks or something like that.
What vaccine vaccine did you take?
The Pfizer one.
Oh, you got Pfizer. I did Pfizer as well, and I'm fine. But there was some weird news today, written somewhere on Facebook by a guy who I usually trust. He said that there is someone who died 3 weeks after the second Pfizer jab. But don't worry. I'm already today. I have 1 month since my second jab, so I'm fine.
Yes, and statistically speaking, it's very hard to.
Of course. The statistics is a science after all. It's not a science I agree with. It's not a science I like because it's the science of nothing. But it's a science. It's better than fake news, and you know what I mean. I mean, statistics at least works with numbers.
Yes,
figures.
and it is very normal when it's normal when you
Yeah.
when you vaccinate millions of people,
Mhm.
some of them to die, but not because of the
No, I'm sure. I mean, okay, yeah, people die, for God's sake. It's tragic, but people die, will die someday, one way or another. I mean, what we cannot prevent. You cannot have 100% safe medicine in this world.
exactly.
I mean, look, we are people, we are educated. You see, this is the reason why such courses of systems theory are good, and they should be taught in all scientific studies, because we understand the notion of signal, system, response, properties, stable, not stable. This is things we understand, so we cannot be so easily scared by fake news, or at least I hope so. Okay. Okay. So again, please be safe. Please do get vaccinated, and please do get more people vaccinated if possible around you, because otherwise this nasty bug is spreading like crazy, and yeah, whatever. Okie dokie. So I'll see you next week.
Yes, thank you very much.
Okay, thank you.
Be safe.
Good
Bye.
evening.
You, bye.
Bye bye.